For this video, you need your notebook and a data booklet. We start topic 2.2 forces. These are the three equations. We have F equals ma, force measured in units of newtons, that's the SI. Mass is in units of kilogram, acceleration units of meters per second squared. The second equation in the data booklet, we have the force of friction, F sub F, is less than or equal to mu sub S. Mu sub S times R. Mu sub S is the coefficient of static friction. It is a unitless number of static friction. You use the coefficient of static friction when an object is not in motion, it's just it rests on a surface. R is the normal force. The normal force is the force that a surface exerts upwards on an object. So if you have a bottle on a table, the force of gravity is forcing the object down. The normal force is holding the object up. Then we have the force of friction, the third equation. The force of friction equals mu sub d times r. Mu sub d is the coefficient of dynamic friction. So d stands for dynamic. And this is the force of friction applied along a surface as an object is in motion. Newton's first law of motion is all about inertia. Inertia. Objects resist a change in their velocity. Objects move with constant velocity or zero velocity unless a force changes their velocity. Objects have inertia, that's mass or resistance to their change in motion. So if the sum, that's what that sigma is, sigma means sum, of all the forces acting on that object is zero, then the velocity is constant. An object traveling constantly at 2 meters per second has a net force of 0. An object moving at 0 meters per second has a net force of 0. Constant velocity and no velocity are the same according to Newton's first law. So what is a force? A force is a push or a pull measured in newtons. The force of gravity is weight. It's the object's mass times the gravitational acceleration. Weight is a vector. M times g equals weight. Weight is a vector. Mass is a scalar. Little g, 9.81, is a vector. Push and pull imply directions, thus forces are vectors. The direction of the weight is always down towards the center of the earth. When we draw objects in this class, I'll put a dot for the object's center of mass. That's the position where all of the force of gravity seems to affect the object, and this weight is drawn straight down. You can use capital W for weight, you can use F sub G. IBEA will not take off either notation for weight. Woo. Okay, if you have a weight of 90 newtons or 90 N, that's the unit for force, your weight can be expressed as a vector, negative 90 newtons. So we will be drawing free body diagrams in this class, and I need you to copy these types of forces. You need to be familiar with them. First, we have tension. Tension is a force exerted by a string or rope. It can only be a pull, it's never a push. Notice that I have an object here and I'm labeling the forces, not in the correct order though. So here we go. I have an object, it has its weight or its force of gravity acting on it from the center. The normal force, the capital R, is what the surface of the object, or the surface the object is on, is exerting back on the object. So the object is in equilibrium vertically. I have a string. String exerts tension and the object can be moved. As the object is moving, there's a force of friction. The force of friction opposes the direction of motion always. So F sub F, the force of friction is exerted between the object and the surface on which the object rests. Force of friction parallel to the contact surface always. The normal force is always perpendicular at a 90-degree angle to the contact surface. It's my 90-degree. Friction and the normal force are mutually perpendicular, which means they are always perpendicular to each other. Friction and the normal force are surface contact forces. Weight is action at a distance force. We'll get more into that for topic 6. So again, weight is always sketched from the center of an object. That's the object's center of mass. The normal is always sketched perpendicular to the contact surface. Friction is sketched parallel to the contact surface, and tension is sketched at whatever angle is given. Usually we want to measure tension with respect to the horizontal, so it would be this angle in here. The resultant or the net force is the vector sum of all the forces acting on a body. So I can see if I have an object being pulled with 50 newtons to the right, and I have a force of friction 30 newtons to the left, Then the net force in the x direction, F sub x, sigma F sub x, that means the sum of all the forces in the x direction. If I choose right to be positive, it's 50 newtons, minus left is negative 30 newtons. Then the net force acting on this object in the x direction is 20 newtons. The resultant force and the weight cancel out, therefore the object doesn't move vertically. You can only directly add forces that are totally vertical or totally horizontal. But what if I have forces that are perpendicular to each other? I have a 50 Newton force acting on this object to the right and a 30 Newton force acting on this object up. So I will have to take the vector sum using the Pythagorean theorem. 30 newtons plus 50 newtons. So 50 squared plus 30 squared, and I would take the square root to get the net force acting on this object. Recall that friction acts opposite to the intended direction of motion and parallel to the contact surface. Suppose we begin to pull a crate to the right with gradually increasing force. We plot the applied force and the friction force as functions of time. So what we see is I'm exerting this tension on the object. I want the object to move, but it doesn't. I can keep applying this force. What's keeping the object in place is the static friction. At some point, however, if I keep applying tension, I'm able to overcome the static friction force. At this point, the object starts to move. Then, as the object moves, I have dynamic friction acting on the object. Dynamic friction is typically lower than static friction. Once you push the object and it's in motion, the force of friction falls, and that becomes dynamic friction. So again, two types of friction, static and dynamic. Every pair of materials, let's say I have a piece of cardboard sliding across steel, every pair of materials will have two coefficients of friction, mu sub s and mu sub d, static coefficient of friction, dynamic coefficient of friction. Again, these are unitless numbers. In addition to the roughness or the smoothness of the materials, the friction force depends, not surprisingly, also on the normal force, how much force is being exerted by the surface onto the objects. The harder the two surfaces are squished together, this is what the normal force measures, the more cold welds can form. We'll talk about cold welding in class. Here are the relationships between the force of friction, F sub f, the coefficients of friction mu, and the normal force, again, provided in the data booklet. So in case I didn't explicitly state it, which I don't think I did, Newton's second law of motion is F equals ma. For an object to change, for an accelerating object experiences a net force. F equals ma is Newton's second law. Newton's third law is pretty obvious as well. For every action force, there is an equal and opposite reaction force. In symbols, if I have an object A and it's exerting a force on B, then B exerts an equal and opposite force on A. The sum of all the forces in the whole universe is 0. So why are there accelerations all around us? Because each force of the action-reaction pair acts on a different mass. That's all I have for topic 2.2. Thanks for watching.